Hello and welcome to Earth Science Lecture 12, Other Igneous Activity. The significance of igneous activity may not be obvious at first glance. However, because volcanoes extrude molten rock that formed at great depth, they provide our only means of directly observing processes that occur many kilometers below Earth's surface. Furthermore, Earth's atmosphere and oceans have evolved from gases emitted during volcanic eruptions. Either of these facts alone is reason enough for igneous activity to warrant our attention. So recall that calderas are large, steep-sided depressions that have diameters exceeding 1 kilometer or 0.6 miles and have a somewhat circular form. Those less than 1 kilometer across are just called collapsed pits or craters. Most calderas are formed by one of the following three processes. First, they could be formed from the collapse of a summit of a large composite volcano following an explosive eruption of silica-rich pumice and ash fragments. An example of this would be Crater Lake in Oregon, which we'll take a look at in just a moment. They could also be formed by the collapse of the top of a shield volcano following a subterranean drainage of a central magma chamber. An example of this would be in Hawaii with our shield volcanoes there. And third, they could be formed by the collapse of a large area caused by the discharge of colossal volumes of silica-rich pumice and ash along what we call ring fractures. An example of this would be Yellowstone. So, pretty quick in the video, I'm actually going to have you stop and watch the Caldera formation video I've linked in the description. This is a really good video because you'll see a visual demo of how a caldera can form using at-home materials such as a balloon and a vat filled with flour. And so you'll see how a caldera can form with something familiar to us. Moving on, let's take a look at an example of each of these three different types of calderas. The first is Crater Lake. Crater Lake, Oregon is situated in a caldera approximately 6 miles wide and more than 1,970 feet deep. This caldera formed about 7,000 years ago when a composite cone named Mount Mazama violently extruded 50 to 70 cubic kilometers of pyroclastic material. With the loss of support, nearly 1 mile of the summit of this once prominent cone collapsed, producing a caldera that eventually filled with water. Later, volcanic activity built a small cinder cone in this caldera. Today, this cone, called Wizard Island, provides a mute reminder of past activity. So here you can see the caldera, known as Crater Lake, and a small pyroclastic cone or a cinder cone in the middle. The second type of caldera was formed by the collapse of the top of a shield volcano. So many calderas can form gradually because of the loss of lava from a shallow magma chamber underlying a volcano's summit. For example, Hawaii's active shield volcanoes, such as Mauna Loa and Kilauea, both have large calderas at their summits. Kilauea's measures about 2 by 3 miles and is 500 feet deep. The walls are almost vertical, and as a result, the caldera looks like a vast, nearly flat-bottomed pit. Kilauea's caldera formed by gradual subsidence as magma slowly drained laterally from the underlying magma chamber, leaving the summit unsupported and allowing it to collapse. Historic and destructive eruptions such as that of Mount St. Helens pale in comparison to what happened 630,000 years ago in the region now occupied by Yellowstone National Park, when approximately 1,000 cubic kilometers of pyroclastic material erupted. This catastrophic explosion sent showers of ash as far as Gulf of Mexico and formed a caldera that was 43 miles across. Vestiges of this event are the many hot springs and geysers in the Yellowstone region, such as Old Faithful. Yellowstone-type eruptions eject huge volumes of pyroclastic materials, mainly in the form of ash and pumice fragments. Typically, these materials are ejected as pyroclastic flows that sweep across the landscape, destroying most living things in their path. Upon coming to rest, the hot fragments of ash and pumice tend to fuse together, forming a welded tuff that closely resembles a solidified lava flow. Despite the immense size of these calderas, the eruptions that produce them are brief, lasting just hours to perhaps a few days. Large calderas tend to exhibit a complex eruptive history. In the Yellowstone region, for example, 3 caldera-forming episodes are known to have occurred over the past 2.1 million years. The most recent eruption, which was 630,000 years ago, was followed by episodic outpourings of degassed rhyolitic and basaltic lavas. In the intervening years, a slow upheaval of the floor of the caldera produced 2 elevated regions that are called resurgent domes. A recent study has determined that a huge magma reservoir still exists beneath Yellowstone. Thus, another caldera-forming eruption is indeed likely, but is not necessarily imminent. Unlike calderas associated with shield volcanoes or composite cones, Yellowstone-type calderas are so vast and poorly defined that many were undetected until high-quality aerial and satellite images became available. Other examples of Yellowstone-type calderas are California's Long Valley caldera and the Valles caldera of western New Mexico. These and similar calderas found around the globe are among the largest volcanic structures on Earth and are hence named supervolcanoes. Volcanologists compare their destructive force to that of an impact of a small asteroid. But fortunately, no Yellowstone-type eruption has occurred in historic times. So this map shown on the right actually shows the Yellowstone National Park and the location and size of the Yellowstone caldera. 3 huge eruptions separated by relatively regular intervals of about 700,000 years were responsible for the 3 different ash layers that are shown. The largest of these eruptions was 10,000 times greater than the 1980 eruption of Mount St. Helens. So please pause the video and watch a brief video on the Yellowstone caldera and what's going on underneath Yellowstone at the current time. The greatest volume of volcanic material is actually extruded from fractures in Earth's crust, called fissures. Rather than building cones, fissure eruptions usually emit fluid basaltic lava that blankets wide areas. In some locations, extraordinary amounts of lava have been extruded along fissures in a relatively short time, geologically speaking, of course. These voluminous accumulations are commonly called basalt plateaus because they have a basaltic composition and tend to be rather flat and broad, as you can see in the images shown. The Columbia Plateau, for example, in the northwestern United States, which consists of the Columbia River basalts, is a product of this type of activity. Numerous fissure eruptions have buried the landscape, creating a lava plateau that is nearly 1 mile thick. Some of the lava remained molten long enough to flow 90 miles from the source. The term flood basalts appropriately describes these extrusions. So, and again, this is possible because it is runny or non-viscous lava. It just oozes out of the fissure and then can travel very far away before it gets stuck and solidifies. Massive accumulations of basaltic lava, similar to those of the Columbia Plateau, occur elsewhere in the world. One of the largest is known as the Deccan Plateau or Deccan Traps, where traps means stairs. It's a thick sequence of flat-lying basalt flows covering nearly 195,000 square miles of west-central India. Most of the lava and materials erupted from a volcano travel through a short conduit that connects the magma chamber to the vent located at the surface. When a volcano becomes inactive, congealed magma is often preserved in the feeding conduit of the volcano and is a crudely cylindrical mass. As the volcano succumbs to the forces of weathering and erosion, the rock occupying the volcanic pyramid shape will be basically eroded away, leaving behind the more resistant volcanic conduit. So what you really see is that the volcano gets eroded away entirely, and all that's left is the solidified magma that was in the central chamber, or the conduit. So you can see that in this graphic here on the left, you see the original volcano, but over very long periods of time, erosion will basically erase the volcano and leave behind just the neck of that volcano. And so what you see in this image here on the right is actually what's called shiprock in New Mexico. It's a widely recognized and spectacular example of these structures, which are called volcanic necks or plugs. More than 1,700 feet high, shiprock is taller than most skyscrapers and is one of many such landforms that protrude conspicuously from the red desert landscapes of the American Southwest. So this to me is one of the coolest things. I mean, if you were to visit this, I mean, okay, it's just a pointy rock, but once you actually understand what it is, I think it's significantly more interesting. So this is basically the conduit of an ancient volcano. Although volcanic eruptions are occasionally violent and spectacular, most magma crystallizes at depth. When magma rises through the crust, it forcefully displaces pre-existing crustal rock, which we call host rock. The structures that result from the emplacement of magma into pre-existing rocks are called intrusions or Plutons. So this slide basically is just going to serve as a bunch of definitions. So the main thing here so far is to remember that anytime we have magma solidifying at depth, we call that feature that it's creating an intrusion or a Pluton. Both are the same thing. Intrusions are known to occur at great depth and in great variety of sizes and shapes. They can be either tabular or planar, meaning they create like sheets like a plane, or they can be massive or blob-shaped. Some of these bodies cut across existing structures, such as sedimentary strata, where others form where magma is injected between the layers. Igneous bodies are said to be discordant, or to disagree with, if they cut across existing structures, and they can be concordant, or to agree with, if they are injected into features parallel to the sedimentary strata. So you'll see an image of what I'm discussing in just a moment, but for now we're just going to go through the different types of intrusions or Plutons, and then review with this single image at the end that kind of brings it all together. Tabular intrusive bodies are produced when magma is forcibly injected into a fracture or zone of weakness, such as a bedding surface. Dikes are discordant bodies that form when magma is forcibly injected into fractures and cut across bedding surfaces and other structures in the host rock, which you can see on the right. So it's something cutting across the structures. By contrast, however, sills are nearly horizontal concordant bodies that form when magma exploits weaknesses between the sedimentary layers or other rock structures. In general, dikes serve as tabular conduits that transport magma upward, whereas sills tend to accumulate magma and increase in thickness. So here's a great example of a dike that's been exposed after weathering. You can see it cutting across the bodies. But here is a sill where magma is getting stuck basically between two sedimentary layers and fills it in. Dikes and sills are typically shallow features, occurring where the host rocks are sufficiently brittle to fracture. They can range in thickness from less than 1 millimeter to more than 1 kilometer. While dikes and sills can occur as solitary bodies, dikes tend to form in roughly parallel groups called a dike swarm. These multiple structures reflect the tendency for fractures to form in sets when tensional forces pull apart brittle host rock. Note that dikes can also radiate away from an eroded volcanic neck like spokes on a wheel, where in this case the active ascent of rising magma generates a fissure in the volcanic cone out of which lava has flowed. Dikes frequently are more resistant and thus weather more slowly than the surrounding rock, which is why we can actually see this exposed dike on the right. In many respects, sills closely resemble buried lava flows. Both are tabular and can extrude over a wide area, and both may exhibit what we call columnar jointing. Columnar jointing occurs when igneous rocks cool and develop shrinkage fractures that produce elongated, pillar-like columns that most often have a hexagonal or six-sided shape. So I think this is one of the coolest features ever of solidifying rocks. A lot of times we might see this columnar jointing where you see just six-sided pillars all over the place. So I just threw this slide in mostly as a fascinating just discussion. Well, by far, the largest intrusive igneous bodies are called batholiths, where bathos means depth and lithos means stone, so stone at depth. Batholiths occur as mammoth linear structures several hundred kilometers long and more than 100 kilometers wide, or 60 miles wide. The Sierra Nevada batholith, for example, is a continuous granitic structure that forms much of the backbone of the Sierra Nevada in California. An even larger batholith extends over 1,100 miles along the coast mountains of western Canada and into southern Alaska. Although batholiths can occur and cover a large area, recent geophysical studies have indicated that most are less than about 6 miles thick. Some are even thinner. The coastal batholith of Peru, for example, is essentially a flat slab with an average thickness of only 1 to 2 miles. Batholiths are typically composed of granitic and intermediate rock types and are often called granitic batholiths. Early investigators thought the Sierra Nevada batholiths was a huge single body of intrusive igneous rock. Today, however, we know that the large batholiths are produced by hundreds of discrete injections of magma that form smaller intrusive bodies, or Plutons, that basically crowd together and breach one another. These bulbous masses are emplaced over spans of millions of years. The intrusive activity that created the Sierra Nevada batholith, for example, occurred nearly continuously over a 130 million year period that ended about 80 million years ago. A batholith is generally defined as a plutonic body having a surface exposed with exposure greater than about 40 square miles. Smaller plutons are termed stocks. However, many stocks appear to be portions of a much larger intrusive body that would be classified as a batholith if fully exposed. So a great example is Half Dome, which you see in this left image. Half Dome is a granitic monolith in Yosemite National Park and is part of the Sierra Nevada batholith. Well, sort of similarly named, we have Laccoliths as well. A 19th century study by G.K. Gilbert of the U.S. Geological Survey in the Henry Mountains of Utah produced the first clear evidence that igneous intrusions can lift the sedimentary strata that they penetrate. Gilbert named the igneous intrusions that he observed Laccoliths, which he envisioned as igneous rock forcibly injected between sedimentary layers so that they arch the beds above them while leaving those below relatively flat. It is now known that the 5 major peaks of the Henry Mountains are not laccoliths but stocks. However, these central magma bodies are the source material for branching offshoots that are true laccoliths, as Gilbert defined them. Numerous other granitic laccoliths have since been identified in Utah. The largest is a part of the Pine Valley Mountains located off the St. George area of Utah. Others are found in the La Salle Mountains near Arches National Park, and then the Abajo Mountains directly to the south. Mount Ellen in Utah's Henry Mountains is one of the 5 peaks that make up this small mountain range. Although the main intrusions in the Henry Mountains are stocks, numerous laccoliths formed as offshoots to these structures. So this little drawing or sketch in the bottom right is extremely important. Here it basically shows each of the different things we've talked about. We see the stock, or basically small batholith here, but magma can become injected into the sedimentary strata, and in this case, if it builds up enough, it can actually warp the strata and create this laccolith feature that we see. And then on the right, we see our dikes and sills. Remember, sills are the intrusions where magma is stuck between the layers of our sedimentary strata, or dikes that cut across them or create more vertical structures. So I actually have a very, very helpful video to link. It shows each of these intrusive structures and how they form in an animated video. It goes fairly quickly, however, so I actually recommend watching it maybe 2 to 3 times just to make sure you can follow everything that happens in the short period of time shown. Most magma originates in Earth's uppermost mantle. The greatest quantities are produced at divergent plate boundaries in association with seafloor spreading, with lesser amounts forming at subduction zones where oceanic lithosphere descends into the mantle. Magma can also be generated when crustal rock is heated and sufficient enough to melt. Recall that igneous rocks are composed of a mixture of minerals. Since those minerals have different melting points, in other words, each mineral has a different temperature at which it starts to change from a solid to a liquid, igneous rocks can melt over a range of temperatures exceeding 360 degrees Fahrenheit. So as rock begins to melt, the minerals with the lowest melting temperatures are the first to melt. If melting continues, minerals with higher melting points begin to melt, and the composition of the melt steadily approaches the overall composition of the rock from which it was derived. Most often, however, melting is not complete. And the incomplete melting of rock is known as partial melting, a process that actually produces most of the magma on Earth. Because most rocks on Earth are not a single composition or a single mineral, they will melt across a range of temperatures, and so we get most of our magma in this way. Partial melting of rock can be likened to a chocolate chip cookie containing nuts that is left out in the sun. The chocolate chips represent the minerals with the lowest melting points because they will begin to melt before the other ingredients. Unlike the chocolate chip cookie, when the rock partially melts, the molten material separates from the solid components. This molten material is also less dense than the remaining solids, and so it rises toward the Earth's surface. Workers in underground mines know that temperatures increase as they descend deeper below Earth's surface. Although the rate of temperature change varies considerably from place to place, it averages about 75 degrees Fahrenheit per kilometer in the upper crust. This increase in temperature with depth is what is known as the geothermal gradient. When a typical geothermal gradient is compared to the curve showing the melting points for the mantle rock periodite, which you see in red, the temperature at which periodite melts is higher than the geothermal gradient at all depths. Thus, under no normal circumstances or conditions is the mantle solid. The mantle is solid, However, tectonic processes trigger melting through various means, including reducing the mantle rock's melting point. So you can see right here, in a very small region, we approach partial melting. Otherwise, everywhere else, we have solid rock. So we mentioned that most magma is produced by partial melting, but we're going to just do a quick kind of recap of the other types of melting that can occur. If temperature were the only factor that determined whether rock melts, our planet would be a ball of molten material covered with a thin, solid overlying crust. This is not the case, because pressure, which also increases with depth, influences the melting temperatures of rocks as well. Melting, which is accompanied by an increase in volume, occurs at progressively higher temperatures with increased depth. This is the result of the steady increase in confining pressure exerted by the weight of overlying rocks. Conversely, reducing confining pressure lowers a rock's melting point. When confining pressure drops sufficiently, decompression melting is triggered. Decompression melting often occurs when hot, solid rock ascends in the upper mantle, thereby moving into regions of lower pressure. Tensional forces along spreading centers promote upwelling where the plates are diverging. This process is responsible for the generation of magma along oceanic ridges or divergent plate boundaries, where plates are rifting apart. Below the crest of the ridge, hot mantle rock rises and melts, generating a magma that replaces the material that shifted horizontally away from the axis of the ridge. Decompression melting also occurs when ascending mantle plumes reach the uppermost mantle. If this rising magma reaches the surface, it triggers an episode of hotspot volcanism. Now this slide should be mostly a review if you've watched the past videos, but along with pressure, an important factor altering the melting temperature of rocks is its water content. Water and other volatiles, such as carbon dioxide, act in a similar way to salt melting ice. That is, water causes rock to melt at a lower temperature, just as putting rock salt on an icy sidewalk induces melting. The introduction of water to generate magma occurs mainly at convergent plate boundaries, where cool slabs of oceanic lithosphere descend into the mantle. As an oceanic plate sinks, heat and pressure drive out the water from the subducting plate and overlying sediments. These fluids migrate into the wedge of hot mantle that lies directly above it. As we've mentioned before, at a depth of about 60 miles, this wedge of mantle rock is hot enough that the addition of water leads to at least some melting. Partial melting of the mantle rock periodite generates hot basaltic magma whose temperatures could exceed up to 2300 degrees Fahrenheit. Mantle-derived basaltic magma tends to be less dense than the surrounding rocks, which causes the magma to rise buoyantly toward the surface. In oceanic settings, these basaltic magmas often erupt on the ocean floor, generating seamounts that may eventually grow into shield volcanoes or islands such as those of Hawaii. However, in continental settings, basaltic magma often ponds beneath the low-density crustal rock. Because the overlying crustal rocks have a lower melting temperature than the basaltic magmas, the hot magma may heat them sufficiently to generate a secondary melt of silica-rich andesite or granitic magmas. If these low-density andesitic or granitic magmas reach the surface, they tend to produce explosive eruptions. Such eruptions occur most often at convergent plate boundaries. Crustal rocks can also melt during continental collisions that result in the formation of large mountain belts. During these events, the crust is greatly thickened, and some crust rock areas are carried to depth where the temperatures are high enough to cause partial melting. The granitic magmas produced in this manner usually solidify before reaching the surface, so volcanism is not typically associated with these collision-type mountain belts. So in summary, magma can be generated by 1. Decompression melting that causes a decrease in pressure, or caused by a decrease in pressure as magma rises. 2. The introduction of water, which lowers the melting temperature of hot rock. And 3. The heating of crustal rock above their melting temperature. So I just wanted to throw in one last slide of this lecture. There's a lot to look at here, and hopefully these little points are legible, but it just shows different regions in which melting is occurring and how magmas are being produced in different scenarios. And it also puts them onto a map so you can see an example of where each is occurring. So this slide is mostly a reference for you if you want to kind of review all of these things we've been discussing recently. But other than that, let's go ahead and close out this lecture with some questions. As always, read each question, pause the video, and then return when you think you have an answer. Number 1. Blank are large, steep-sided depressions that have diameters exceeding 0.6 miles and a somewhat circular form. Okay, so this was our first topic of this lecture. That was the calderas. If they have a smaller radius, in other words, less than 0.6 miles, we would refer to them as craters. But since they are large enough in this example, we call them calderas. Question 2. The region labeled Z in the attached figure could eventually be preserved as part of a blank on the surface of the Earth. So in other words, what will Z form? Okay. Well, in this case, it's a solidifying magma body or intrusion, so we're going to see that solidify as a batholith. These occur as mammoth linear structures, very long, with a very big width as well. And so you can see here, all of this central chamber that's solidifying, this together will form a batholith. Number 3, most magmas are formed by what? All right, well, we mentioned this just a little bit ago, but it is partial melting. This is the incomplete melting of rocks, which is a process that does produce most of our magmas. And it does this because, again, remember that rocks are made out of multiple different minerals. Each mineral melts at a different temperature. And last but not least, number 4. Water causes which of the following related to magma formation? All right, and in this case, we just learned that rocks will melt at a lower temperature if water is introduced, which is why when a plate is subducting underneath another, once it gets down to about 60 miles, it can trigger some melting because of the addition of water. All right, as always, thanks for watching and have a great day.